Now we will discuss the effective value for the periodic wave in the last part of this lecture. Firstly, let's introduce the definition of the effective value for the periodic wave. We suppose IT is a periodic wave. It needn't to be a sine wave. A periodic wave is enough. We should calculate the energy delivered by IT to the resistor in one period. The energy can be expressed as the time integral of the square of time I from 0 to t. Once the waveform of I is given, we can calculate the energy. This analysis is a little complicated. We might as well use a equivalent dc to express the energy delivered by the periodic wave. Now we suppose the energy delivered by the equivalent dc in the same period of capital T equals the energy delivered by the periodic wave. Although the direct current has no cycle, we still discuss the energy delivered by the current from 0 to capital T. According to the discussion on sine wave, we can know the energy equals the square of I times R times capital T. If we want to use this dc to represent a periodic wave, we should make them equal. So we can get that dc equals the square root of 1 over capital T times the integral of the square of I from 0 to capital T. From the expression of the dc, which is used to represent the energy delivered by the periodic wave, we can see it's a square root, and it's a mean inside the radical sign. The mean part inside the radical sign contains the square of I. So this operation is called RMS. The discussion is on current. The discussion on voltage is similar. By remembering the meaning of RMS, you can easily remember the effective value for periodic wave. The reason why it's called effective value is that the thermal effect of the current or the voltage on the resistor is the same as that of the periodic wave. Next, let's do exercise. This voltage wave is a periodic one whose cycle T is 3 seconds. According to the definition, its effective value of all RMS value is the square root of 1 over 3 times the integral of the square of u from 0 to 3. U can be divided into 3 parts from 0 to 3. It equals 1 from 0 to 1, 2 from 1 to 2, and 0 from 2 to 3. So the integral can be divided into 3 parts. It equals 1 over 3 times the integral of the square of 1 from 0 to 1 plus the integral of the square of 2 from 1 to 2 plus the integral of the square of 0 from 2 to 3. We can know that the effective value is 1.29 volts. Now let's discuss RMS for sinusoid at the end of this lecture. For a sinusoid whose amplitude, angular frequency, and initial phase angle are given, we can calculate its effective value with the definition. I equals the square root of 1 over capital T times the integral of the square of Im times the square of sine omega t plus psi from 0 to capital T. We can move the constant Im out of the radical sign, and then the Rms equals this. By applying trigonometric equivalent transform, the square of sine equals 1 minus cosine 2 times omega t plus psi over 2. The integral of sine t from 0 to capital T equals 0, so the integral of sine 2t from 0 to capital T equals 0. So the integral of this part from 0 to capital T equals 0. So the expression equals Im times the square root of 1 over capital T times the integral of 1 over 2 from 0 to capital T. the result equals Im over the square root of 2, or 0.707 times Im. In other words, the amplitude of sine wave can be represented as the square root of 2 times the effective value. This is very important. After the discussion, we know that a sinusoid can be written as a form with the square root of 2 times the effective value, angular frequency, and the initial phase angle. So the three elements are effective value, angular frequency, and the initial phase angle in the following discussions. Well, this is the end of this lecture.